In the autumn of 1918, on the Macedonian front of the First World War, a Polish physician named Ludwig Hirschfeld and his wife Hanke were standing in the middle of one of the strangest laboratories ever assembled. Wounded soldiers from a dozen different armies were passing through the same field hospitals: French, British, Serbian, Russian, Indian, Vietnamese, Greek, and more, and the Hirschfelds realized they had something no one had ever had before: a single controlled setting where they could test the blood of thousands of men from wildly different corners of the world using the exact same method. What they found broke the assumption doctors had quietly held for almost 2 decades. Blood type was not simply an individual trait scattered evenly across mankind. It shifted, sharply and consistently, from population to population. European soldiers carried one pattern. Indian and Vietnamese soldiers carried another. The numbers moved like a dial as you crossed from one army's tents to the next, and the Hirschfelds published what became one of the first population-level maps of human blood ever made. It was 1919. The idea that blood might carry the fingerprints of migration, ancestry, and deep history was born on a battlefield out of desperation and curiosity, and it has never stopped being confirmed. Because more than a century later, when modern population geneticists went back and did what the Hirschfelds could only dream of, testing blood markers across tens of thousands of people spanning every continent, drawing on ancient DNA, hospital records, and decades of published population surveys, the picture that emerged was not just a confirmation. It was staggering in ways that even seasoned researchers did not expect. In some populations, one blood type does not simply dominate, it approaches total saturation, wiping out the other letters almost entirely. In others, a marker considered rare across the whole human species spikes to levels 10 times the global average. And buried inside data, most people have never thought twice about lies a gap in modern medicine wide enough to affect how chemotherapy and other critical drugs are dosed for hundreds of millions of people alive right now. This is the story of what 100 years of blood typing has quietly revealed about where we come from and what it is still telling doctors today, whether they are listening or not. To understand why this matters, you have to start with how little the average person actually knows about their own blood type beyond the letter on the card. Blood type was only discovered in the first place in 1900 and 1901, when the Austrian physician Karl Landsteiner noticed that mixing blood from different people sometimes caused the red cells to clump together into a deadly sludge, and sometimes did not. He sorted people into groups, A, B, and O, and a colleague later added the fourth, AB. Before Landsteiner's discovery, transfusions were a coin flip with a patient's life, sometimes saving them, sometimes killing them within minutes, and nobody understood why. Landsteiner's work explained the mystery and eventually won him a Nobel Prize in 1930, decades after his original discovery, once the medical world had fully caught up to what he had found. Before that recognition, his early papers were treated as a useful curiosity rather than the foundation of an entire branch of medicine. And it took the mass casualties of the First World War, with battlefield surgeons desperately needing a reliable way to match donors to wounded soldiers, to turn blood typing from an academic footnote into a matter of daily life and death. But for decades afterward, the letters were treated purely as a medical convenience, a matching system for transfusions and nothing more. Nobody was asking why some populations leaned one way and others leaned another. It took a world war and a pair of curious doctors to even raise the question. And once the question was raised, it never really went away, because every new data set, every new country surveyed, every new ancient skeleton tested, kept adding pressure to the same conclusion. Blood type is not random noise, it is a record. It is shaped by who your ancestors were, where they lived, what diseases nearly wiped them out, and which populations they mixed with or stayed isolated from for thousands of years. And nowhere is that record written more dramatically than in the indigenous populations of the Americas, where the pattern is not just strong, it is almost absolute. Type O is, on a global level, the most common blood type on the planet, and by itself that fact tells you almost nothing interesting. It is the universal donor type, the blood hospital stockpile, because it can be given to nearly anyone in an emergency, and averaged across all of humanity. It sits at a healthy but unremarkable majority. But averages hide everything, and the moment researchers stopped looking at the whole species and started looking population by population, the picture around type O stopped looking like chance. Among numerous indigenous groups of the Americas, from communities in the North American plains and Southwest to populations across the Andes and the Amazon basin, type O frequency does not simply lead, it approaches, and in some documented groups effectively reaches total saturation. Multiple population surveys conducted across the 20th century found indigenous South American communities, including groups in Peru and Bolivia, where researchers could not locate a single confirmed individual carrying type A or type B blood. Not a rare occurrence, not a handful of outliers, none at all across sample after sample, generation after generation. If blood type were purely a random coin flip passed down through families with no historical shaping, this would be roughly equivalent to gathering 50,000 people in a stadium, asking each of them to flip a coin, and watching every single one land on heads. It simply does not happen through chance alone. Something forced this outcome, and researchers have spent decades chasing the explanation. The leading theory centers on what geneticists call a founder effect, layered on top of a genuine bottleneck in human history. The ancestors of the indigenous peoples of the Americas crossed from Siberia into Alaska in waves beginning somewhere between 14 and 20,000 years ago, and the population that made that crossing, along with the harsh, isolating journey southward through Beringia and then down through 2 entire continents, was almost certainly small. A small founding population carrying a narrow set of blood type genes would pass that narrowness down to every single descendant. And if type A or type B genes were rare or absent in the founders, they would remain rare or absent in the billions of descendants that followed, no matter how many thousands of years passed. Layer onto that the near total isolation of the Americas from the rest of the world for roughly 10,000 years before European contact, with no major waves of migration diluting the gene pool the way they did continuously across Eurasia and Africa, and you get exactly the kind of frozen genetic snapshot researchers keep finding. Some scientists also point to disease pressure, the idea that ancient epidemics may have disproportionately affected carriers of certain blood types, tightening the distribution further with each wave of illness that swept through isolated populations with no prior immunity, a phenomenon tragically repeated on a massive scale after European contact. Whatever the precise mixture of causes, the pattern itself is not disputed. It is one of the cleanest, sharpest population-specific genetic walls anywhere in human biology, and it set researchers up to ask an obvious next question. If type O could draw a wall this absolute in one part of the world, what were type A and type B doing everywhere else? And were they scattered randomly, or were they leaving a trail of their own? Type A turned out to hold a gradient so smooth it was almost suspicious. Across populations of European descent, type A frequency tends to average somewhere in the low 40s as a percentage, making it, alongside O, one of the 2 dominant types across the continent. But travel east, out of Europe and across the vast stretch of Eurasia, and that number does not fall off randomly. It declines in a smooth, consistent slope. Move into East Asian populations, and the frequency of type A drops noticeably, often into the high 20s. Continue into parts of sub-Saharan Africa, and it falls further still. This is not scatter. Scatter would bounce unpredictably around an average. What the data shows instead is a slope, a gradient that thins the further you travel from a particular region, almost as though type A radiated outward from somewhere in western Eurasia and grew paler with distance, the way ink spreads and fades through water. Researchers studying ancient DNA have connected this gradient to the deep genetic contributions of early farming populations that expanded out of the Fertile Crescent into Europe beginning roughly 8,000 to 9,000 years ago, spreading agriculture and their genes across the continent in a slow demographic wave that reshaped the blood of everyone who came after them. Type B tells an even sharper story because unlike type A's smooth continental slope, type B spikes hard in one specific place. In Western Europe, type B is genuinely uncommon, often found in less than 10% of the population in countries like Ireland, Spain, or France. But trace a line eastward across the immense grasslands stretching from Ukraine through Kazakhstan and into Mongolia, and the frequency of type B does not simply rise, it surges. Among Kazakh, Uzbek, and Mongolian populations, published surveys have found type B frequencies climbing into the 30 to 40% range, 3 or 4 times higher than what you would find in London or Lisbon. Something concentrated type B across thousands of miles of open steppe, while leaving the western edge of the same landmass almost untouched. And the geography offers a compelling clue. The corridor where type B peaks is not just any strip of land, it is the Eurasian steppe, the great historical highway along which nomadic and pastoral peoples moved for thousands of years, driving herds, following seasonal water sources, and periodically erupting outward in waves that reshaped the populations they encountered. Blood, unlike a name in a chronicle or a line on a map drawn by the victors, does not get edited by history. It simply gets passed down, generation after generation, carrying a record of every ancestor who contributed to a lineage. When a population moves and mixes with the people it encounters, it leaves a genetic trace in the local distribution that researchers can still detect 1,000 years later, if they know where to look. The most dramatic example, historians and geneticists point to, is the 13th century Mongol expansion. In the span of a few generations, starting under Genghis Khan around 1206, a coalition of steppe peoples built the largest contiguous land empire in recorded history, stretching from the Pacific coast of China to the edges of Central Europe and the Middle East. History remembers this in the language of conquered cities and toppled dynasties, but population genetics suggests it also left a quieter biological signature, because wherever those armies and the populations that followed them settled, they carried their steppe ancestry, and with it, their blood type frequencies, into the peoples they conquered and absorbed. Several genetic studies published in the last 2 decades have identified a distinct Y chromosome lineage carried by a strikingly large share of men across a huge stretch of Central Asia. A lineage some researchers have connected to Genghis Khan's own bloodline given its age and pattern of spread, and it maps remarkably well onto the same corridor where type B frequency runs highest today. You are, in a very literal sense, looking at genetic evidence of an 800-year-old migration still legible in the blood of people alive right now, a trail left not by choice but by conquest, movement, and generations of intermixing along a single ancient highway. If the letters most people learn as childhood trivia could hold this much buried history, researchers began to wonder what the parts of blood almost nobody has heard of might be hiding. And that search led directly to the Rh factor, the plus or minus sign tacked onto the end of every blood type. Rh-negative blood is genuinely rare across the human species as a whole. In populations of European descent, it appears in roughly 15% of people. In sub-Saharan Africa, that figure drops to somewhere between 3 and 8%. And in East Asian and Indigenous American populations, it very often falls below 1%, rare enough to be nearly absent across most of the human family tree, which is exactly why the numbers coming out of a small population tucked into the western foothills of the Pyrenees Mountains, straddling the border of northern Spain and southern France, looked at first like a data error. The Basque people speak a language unrelated to any other known tongue on Earth, a true linguistic isolate with no confirmed relatives, and when researchers tested their blood, Rh-negative frequency came back at roughly 25 to 35% depending on the specific community sampled, more than double the European average and many multiples above the global norm. A single ancient population, walled off by mountains and by a language nobody else on the planet can claim, carrying a blood signature that sets it apart from virtually everyone around it. The explanation that has survived the most scrutiny is that the Basques are not an anomaly at all, but a remnant, a surviving fragment of the population that lived across Western Europe before farming ever arrived. Roughly 8,000 years ago, agriculture began spreading westward out of Anatolia, and the farmers who carried it did not simply pass through Europe. They settled, intermarried, and multiplied, and over thousands of years their genetic signatures spread across the continent like a rising tide, gradually diluting and displacing the deep genetic makeup of the hunter-gatherer populations, who had lived there for tens of thousands of years before them. That older signature was overwritten almost everywhere on the continent, but the Pyrenees acted as a partial barrier, and behind it, protected by geography and by a language that never bent to the newcomers, a pocket of that pre-agricultural population held on more completely than almost anywhere else in Europe. Modern genetic studies of Basque ancestry broadly support this picture, showing the Basques carry an unusually high proportion of pre-farming European ancestry compared to their neighbors, and their striking Rh-negative frequency lines up with that older genetic layer sitting closer to the surface than it does almost anywhere else on the continent. Two completely different lines of evidence, a language and a blood marker, appear to be telling the same story from two different directions. If blood could preserve the memory of a vanished European population, researchers reasoned it might preserve other memories too, memories written not by migration or mountains, but by disease. And that question led straight to a blood group so obscure that many working physicians have never had reason to think about it, the Duffy blood group. The Duffy antigen is a protein sitting on the surface of red blood cells, and most people around the world carry it without ever knowing it exists, because it does not show up on a routine blood type card the way A, B, or Rh does. There's a variant known as Duffy-null, in which the antigen is essentially switched off and absent from the surface of red cells entirely, and in populations with deep West and Central African ancestry, a category that includes the overwhelming majority of African Americans, given the documented origins of the transatlantic slave trade. The Duffy-null variant appears in somewhere between the high 60s and mid-90s as a percentage of individuals tested. Meanwhile, in populations of European or East Asian descent, the same variant appears in less than 1% of people. This is not a modest statistical difference. It is one of the starkest population divides found anywhere in human genetics, and unlike the type O wall in the Americas, which still lacks a single clean explanation, this pattern has one that researchers consider essentially settled malaria. Specifically, a form of the malaria parasite called Plasmodium vivax needs to grab onto the Duffy antigen like a doorway in order to force its way into a red blood cell and establish an infection. Switch the antigen off, and the parasite arrives at the cell with no handle to grip, no way in. Across a wide belt of West and Central Africa, where vivax malaria circulated for thousands upon thousands of years, carrying the Duffy-null variant was not a genetic quirk. It was the difference between surviving to have children and dying young from repeated infection. Over enough generations, natural selection did exactly what natural selection always does under that kind of unrelenting pressure. It pushed those populations toward the protective variant with such consistency that today it defines them almost completely. This is evolution recorded directly and permanently in living blood. A molecular scar left behind by an ancient, generations-long war against a parasite, a war whose outcome is now written into the red cells of hundreds of millions of people who have likely never once thought about it. But the discovery carries a second, far more immediate edge, because the Duffy antigen does not only decide whether a malaria parasite can force its way into a cell, it also happens to influence a completely unrelated blood measurement, the routine white blood cell count that doctors use every single day to monitor patients. People who carry the Duffy-null variant tend to naturally run a lower baseline neutrophil count, a condition long recognized in medical literature and sometimes referred to as benign ethnic neutropenia, without it indicating any underlying illness or weakened immune function at all. The problem is that most of the reference ranges doctors use to decide whether a patient's white cell count is dangerously low, ranges that determine whether a chemotherapy dose gets reduced, whether an antiretroviral or antipsychotic medication gets paused, or whether a patient gets flagged for a bone marrow workup, were built primarily from clinical trial populations of European descent, in which the Duffy-null variant is almost entirely absent. Multiple studies published over the past 2 decades have documented exactly this imbalance, describing how thin the representation of African ancestry populations was in many of the trials that shaped modern dosing and monitoring standards. Laid over the genetic data, the implication is uncomfortable and hard to wave away. For certain drugs and certain monitoring thresholds, standard practice may have been quietly and visibly miscalibrated for large populations for decades, not through any single act of malice, but simply because the reference bodies used to build the standard did not carry the full range of human blood variation. It is not a pattern confined to a museum or an old paper. It is a pattern sitting inside pharmacies and hospital labs right now, still shaping decisions made today. From here, researchers push the question back even further, into the deep and often contested question of ancient population origins, because blood type is not only readable in the living. For most of the 20th century, scientists assumed blood, antigen information, simply could not survive in old bone, that it decayed and vanished without a trace. That assumption began breaking down in the 1970s and 1980s as researchers developed techniques to recover ABO antigens preserved in ancient bone, teeth, and mummified soft tissue. And Egyptian mummies became one of the most studied populations of the ancient world precisely because of how well preserved so many remains are. Multiple ABO surveys conducted on Egyptian mummies and skeletal remains spanning thousands of years of Nile Valley history have found blood type distributions that, in various studies, show notable overlap with populations both to the north across the Mediterranean and to the south along the African interior. A finding researchers describe as reflecting Egypt's long history as a genuine crossroads civilization, one that traded with, migrated alongside, and was periodically conquered by neighboring populations on every side across thousands of years. It is worth being careful here, because the deeper question of ancient Nile Valley population origins remains a genuinely debated topic among historians, archaeologists, and geneticists, with different lines of evidence, sometimes pointing in different directions depending on the time period. The region of Egypt sampled and the method used. What the blood and ancient DNA evidence broadly supports is a picture of Egypt as a place shaped by connections running in multiple directions at once, north into the Mediterranean world and south and west into the African interior, rather than a fully isolated or uniform population at any point in its long history. Some researchers have pointed to the Green Sahara period, when the region that is now the world's largest hot desert was instead a savanna crossed by rivers and lakes for thousands of years, before it began drying out roughly 5,000 to 6,000 years ago, as a corridor that allowed populations across a huge stretch of northern Africa to move, mix, and exchange genes long before the desert became the formidable barrier it is today. What all of this adds up to, across a Mongol-era steppe migration, a French Pyrenees mountain range, a West African disease corridor, and a Nile Valley crossroads civilization, is not a story about race being biologically real in the way it was once crudely imagined. It is closer to the opposite. Every population geneticist working in this space today will tell you the same thing, that human genetic variation is not neatly organized into a handful of discrete, boxed-in categories. It is one continuous, overlapping river of variation flowing all the way back to a single ancestral population that walked out of Africa roughly 60,000 to 70,000 years ago, carrying within it the seeds of every blood type, every marker, every gradient that would later spread and thin and concentrate across the different environments and histories that different groups of humans encountered along the way. Blood type describes populations and their histories in broad strokes, shaped by founder effects, disease pressure, and migration. But it does not trace any single living person back to any single specific ancestor, and it was never designed to. Consider what these numbers actually mean on the ground, right now, today. In a rural clinic somewhere in the Andes, a nurse could draw blood from 100 patients and find type O in nearly every single vial, a signal so uniform it looks almost impossible, a wall standing exactly where pure randomness would have predicted a scatter. In a hospital in Central Asia, the balance tips the other way, type B appearing again and again, a quiet echo of horsemen who crossed the steppe 8 centuries ago and never could have known they were leaving a genetic marker in the blood of people not yet born for hundreds of generations. And in a modern oncology ward anywhere in North America or Europe, a patient carrying the Duffy-null variant might have their chemotherapy dose adjusted, delayed, or reduced based on a white blood cell reference range built decades ago from a population that essentially never carried that variant in the first place, a small but real gap between the science built and the patients it now serves. This map was never confined to a textbook or a museum case. It has been sitting inside people this entire time, read every single day by machines and clinicians who, for the most part, have no idea the deeper geography is even there. So the 2 letters and the small plus or minus sign printed on your donor card, or on the paper. A nurse hands you after a routine test were never really trivia in the first place, no more meaningful than a shoe size. They are the tail end of a sentence that began writing itself before agriculture, before cities, before anyone had a word for a nation or a continent. When you first learned your own blood type, it was almost certainly framed as nothing more than a random accident of genetics, a coin flip with no story behind it. Knowing now that it might trace a founder population crossing into an empty continent, a survived epidemic, a mountain refuge that outlasted an entire demographic wave, or a molecular war fought against malaria for thousands of years, does it change how you look at those 2 letters, sitting quietly on a card in your wallet, waiting for someone to finally ask what they are actually trying to say?